There you go. It's recording. Okay, some reminders that Rachada sent. I haven't had a chance to incorporate yet. I don't know if you can see that, but we posted the mid-semester grade distribution. Just remember that that's out of 41 points, 42 points, 42 points. And this includes 3 labs, 2 homeworks, 1 exam, which is less than 50% of the course. And that grade distribution you can find on the website, right?
It's on the front page.
Yeah, if you go to the front page. We should actually put it in a place that's separate from the front page also. I guess you'll move it somewhere over here later on. Maybe under, I don't know where. Maybe grades. So if you look at this is what I had assigned for your mid-semester grades. You should be able to see pluses and minuses in your, what is that called? You added that also, right? To the, where do we add the grades to?
Oh, Blackboard.
Blackboard, yes. That piece of software doesn't work very well, so.
No, it doesn't.
It doesn't, good. Yeah, but that's the only place where we post the grades right now. So you should be able to see minuses and pluses. And you also have your mid-semester grade that I entered. Minus plus means you're actually at the border of A and B, if you will, if the curve looks like this. Now, I know that you're not here for grades, but I want to explain to you how I actually came up with the grades. So basically, these are A's, and some of the A minuses are actually, I gave A's for mid-semester grades, but you're at the lower end of A's. And if you've got a B plus, if you see a B plus in your Blackboard grade, do you see that?
Yeah.
Yeah, some of you would see B pluses. That means that you're at the higher end of B's, which means that you're closer to A's actually. If it's a B minus, you're at the lower end of B's. If it's C plus, you're at the higher end of C's. C is a solid C, I guess. And then so on. Make sense? And this is what the distribution looks like. And this is where, these are where the buckets go, right? Is that right, Rachada?
Yeah.
Okay. Yeah. And you can see this. This is basically based on a curve, based on all of these results so far. This doesn't include extra credit so far, so if you've done extra credit, it'll very likely bump you up somewhere. We're not going to give you negative grades for extra credit for the labs. And yeah, that's it, basically. Keep in mind that these are out of 42, and the class will be out of 100. Okay. So there's still a lot to go. For this next lab, checkoff will be very important, because actually 50% of your grade will be determined by the checkoff. 50% of your grade will be determined based on the test we run. So definitely go to the lab checkoff as early as you can next week. Do not wait until next Friday. Otherwise, there'll be a long backlog during the Friday lab. Okay? And the last thing is, for all the labs, we specify that as much as possible in the lab handout. Follow the specification in the lab handout. If there are any changes to the specification, they will be announced at Piazza. And whenever there is a change to the specification, because there is a correction, for example, which happens because there's human error, right, when we prepare the labs, Rachada and other TAs will endorse an answer, potentially, or give an answer, and send the email through Piazza. Is that right, Rachada?
Yeah.
Okay. So that's how we do the corrections to the labs. So Piazza is the main place where labs are corrected, but TA's answers are the definitive answers. TAs can later correct their answers too, but their answers are the definitive answers. Those answers should be endorsed. Does that make sense? Yes.
There are 2 things. If there's a good answer, we endorse them. If there's any changes to the specification, you email you guys.
Okay. So follow Piazza is a good suggestion. Make sense? Okay. Now let's go back to the lecture. Okay, we're going to cover more caching today, and probably in the next lecture too. Given that people have worked on this for 50 years, it's probably a good idea to dedicate 3 lectures or so, right? Or more. Okay, reminders, one of your labs is due today. I hope you'll be doing the extra credits. Homework 5 is due March 26th, and lab 5 will be out today. It's going to be due April 4th. We're going to do a switch in lab 5. That's lab 5, right? Yeah, you have 3 more labs. We're going to do a high-level simulation of the processor that you've designed. You'll see the difference. And you're going to be implementing branch prediction and caching in the high-level simulation. High-level meaning C-level simulation. So you don't actually need to model every cycle accurately, model the gates accurately. That enables you to do very design trade-offs at a high level. But we can talk about that later. Okay, this is what I told you earlier. Okay, these are the readings for today and the next lecture, so hopefully you're doing these. We stopped at the replacement policy for set associative caches. Remember, we talked about set associativity. And set associativity is a way to accommodate more blocks within a set, such that you don't run into these conflict misses. If you're accessing A and B, blocks A and B, and they happen to map to the same cache set, if you have a direct map cache, you'll get misses for both blocks if you're doing AB, 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 AB. If you increase the associativity, if you enable more blocks to be stored at the same index, then you have more flexibility in how many blocks you can store in the same set. And this leads to better hit rate in general, as we've discussed in the last lecture. But this also leads to the question of what do you replace? Because now multiple blocks can be present in the same set. And if you want to insert another block, what do you replace from that set? That's the idea of the cache replacement policy. And we talked about the least recently used replacement policy and its approximations in the last lecture. We briefly talked about the random replacement also. And I've told you that sometimes it's a good idea. And I've actually given you an example of when it's a good idea also, right? For example, for a reference pattern where you have a 4-way associative cache, but you're actually referencing 5 blocks in a manner that's such that you keep re-referencing them, A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. LRU is a terrible replacement policy because you will get a 0% hit rate on that one. Okay, this is called set thrashing. Basically, this behavior that I just described is called set thrashing. You're really thrashing that set, meaning that the working set of this program for this particular set is larger than the associativity. You have 5 things to store in that set, and you keep accessing it. What is working set? Working set is the amount of data, if you will, that you're accessing in a given amount of time, in a certain amount of time. In this case, A, B, C, D, E are accessed in sequence within some time, and your set cannot accommodate all A, B, C, D, E. You're thrashing that set. So if this is happening, well, I guess I have the question over here. I have the example over here. If this is happening with the LRU policy, you get 0% hit rate. But random replacement policy is better when such cases actually occurs, when thrashing occurs. And I'll let you figure out the hit rate if you actually randomly replace something. That's fun. And that, I mentioned that this could be an exam question or a homework question. Well, it's not in your homework, so it could be an exam question. Okay, so basically, in this case, it's much better to have random replacement. In fact, you could think of some other replacement that maintains some blocks. In this case, it just makes sense, for example, to maintain A, B, C, D in the cache. Then you get 80% hit rate. Right? It's better than random if you can somehow figure this pattern out. And that's actually a promising direction, somehow identifying different kind of access patterns and adjusting the replacement policy to those different kinds of access patterns. So in practice, so in this particular case, random does better than LRU. But in practice, obviously, the performance of the replacement policy depends on the workload. And there have been many studies that show that average hit rate of LRU and random replacement are actually similar across many workloads, if your associativity is small enough. So people have proposed hybrid replacement policies. This is one paper we had written in 2006 that talks about MLK over cache replacement, which I'll cover later. But basically, it also introduces the concept of doing hybrid replacement. And the idea is you have some sets dedicated to LRU and some other sets dedicated to random replacement, and you try to figure out which one is doing better. And depending on which one is doing better dynamically, you apply the better replacement policy to the remaining sets. That's the idea of set sampling. You fix some sets to do LRU replacement, you fix some other sets to do random replacement. Actually, you can fix both sets. You can fix the same set of sets, if you will, to do both kinds of replacement, figure out which one is doing better, and the remaining sets follow that policy. Does that make sense? You sample basically across the entire cache some sets, let's say 32 sets out of 1024, and those compete for, decide between LRU and random, and then depending on whichever one is doing better dynamically, you pick the one. This is similar to dynamic branch predictors. You could do it on a per set basis also, but then the cost is very high. Okay, if you want to learn more about it, I'd suggest you read this paper. It's actually a fun paper to read. We'll come back to that. Optimal replacement policy, I talked about this too, so I'll go over this really quickly. This is a seminal paper that introduced optimal replacement, actually within the context of virtual memory. We'll get back to this, but page replacement is very similar to cache replacement. In virtual memory, physical memory is limited. Right? Physical memory is really a cache for the disk, if you will. And whenever you run out of physical memory, you need to replace something. And that replacement policy is similar to cache replacement, except we'll see some differences in a few slides. The idea of optimal replacement was developed within the context of virtual memory. How do you actually manage physical memory as a cache? And what is optimal replacement? Basically, replace the block that's going to be referenced furthest into the future by the program. Obviously, you cannot implement this because you need to know the future for this. You can potentially predict it. And LRU is a predictor for this, actually. LRU assumes a particular reference pattern, and it's a predictor for this. But it may not always work if the reference pattern is not cyclic, like we've discussed. How do you simulate this is another interesting issue, which we'll not talk about. But one question, is this optimal for minimizing miss rate in a cache? Yes? Yes, it's optimal, actually. It does minimize the miss rate. But is it optimal for minimizing execution time? Did I hear no?
It depends.
It depends. I guess that's true, but optimal is a strong word, right? Optimal means for every case does it minimize execution time.
What if the logic is in the critical path?
Yeah.
Then increase the call cycle.
Oh, I see, compared to other policy. Well, that was not what I was asking. Yes, this can be very complex, assuming you can implement it, yes.
That not always, because can it always just reduce down to like where like the next thing that you need is not really far away, but you just have a really small working set size and somehow they thrash each other? Can that still happen?
Well, not with this one, right? Because you'll always replace the thing that you're going to reference furthest into the future. So it does minimize the miss rate.
Okay.
But miss rate is not the same as execution time, as we discussed. Meaning, for example, some of these misses may be more costly. So let's say you have A, B, C, D, E, and you somehow figure out, maximize the hit rate, but one of the blocks is extremely costly. You always want to keep that in the cache, regardless of whether or not it's referenced furthest into the future. Because that block takes 1,000 cycles to fetch back from memory, whereas all the other blocks, A, B, C, take 10 cycles to fetch from memory. Make sense? That's the difference between execution time and miss rate. You may be optimizing for miss rate, but execution time really depends on the latency to refetch the block, or the cost of refetching the block, if you will. So this optimal doesn't take into account that cost. It takes into account only the hit rate or miss rate. Make sense? Yeah. So this will be a theme. Keep this in mind. Whenever you're optimizing for miss rate, you may be actually increasing execution time because the different blocks in the cache have different costs. Okay. Well, yes. There are many reasons. We've talked about those reasons in the last lecture. And miss overlapping is another reason. For example, if a miss is overlapped with many other misses, then its cost is less because you're really amortizing that cost across many misses. Yes?
But you really want to optimize execution time, right?
Exactly,
So
yes.
you could have some optimal thing that takes this and then adds a weighing of how
Yeah.
long it would take to.
That's it. That's actually great. If you can come up with such an optimal policy, even if it's not implementable, that's a good paper to publish. Maybe you can think about that. It's tough to do that. It's very tough to do. Come up with an optimal that takes into account the latency as well. But yeah, we'll get back to this. This paper actually shows that this policy is not optimal for minimizing miss rate, given that you have miss overlapping in current out-of-order processors. Because a miss that happens alone by itself is much more costly than a miss that happens with many other blocks in parallel. Okay, we'll get to that. Oh, I promised you that cache replacement is similar to page replacement. Basically, physical memory is a cache for disk, right, in a demand page system. And physical memory is usually managed by system software via the virtual memory subsystem. And you can think of the page table as a tag store for the physical memory data store. Obviously, page table does other things like access protection bits as well, but it's really a tag store for the physical memory data store, right? Physical memory contains some data store, and page table shows where a virtual page is mapped. The key difference is, well, caches, as we have defined them so far, are managed in hardware, whereas this is managed in software, mostly. It's accelerated in hardware with TLBs, which is a cache for a cache, I guess. And the number of blocks in cache is usually much, much smaller than the number of blocks in physical memory. Right? If you have 4 gigabyte physical memory and 4 kilobyte pages, you have many, many blocks. Right? I guess you could do the 2 to the 30 divided by 2 to the 10, right? 2 to the 20 blocks. That's 1 million blocks. Whereas biggest caches today have on the order of maybe 10,000 blocks at most. Which means that how do you actually find the replacement candidates in physical memory? In a set associative cache, you look at only 4 things, right? Well, in a 4-way associative cache, you look at only 4 things to figure out which one should be replaced. In an n-way associative cache, you need to look at n things. What about the page table? If you would like to replace a page from the entire physical memory, do you look at all of the pages in physical memory, all of the frames in physical memory? That's a lot of frames. That's 2 to the 20 frames, right? You don't want to do that. Now you can organize physical memory similarly to a cache. You need to stretch your mind a little bit. So far, when we talked about physical memory, it was like a direct map cache, right? Well, it's not direct map actually. It's fully associative cache, right? We don't have the hardware to do that, but any virtual page can go to any physical location. In that sense, it's fully associative. Which means that you need to find the replacement candidates relatively efficiently among all of those pages that are currently in physical memory. So let's say you want to bring another page into physical memory, but all of those pages are occupied. Then the key question is, how do you actually find the page to replace? And people have developed algorithms for this, which I'll not get into. But one popular algorithm is the clock algorithm. And obviously, it's very hard to examine 2 to the 20 physical frames and figure out which one is to be replaced. But the idea of clock algorithm is to replace the ones that are not recently referenced. So you could do LRU across all of the 2 to the 20 pages, and that would be very complex. Right? You don't want to do that. Instead, you could do something like not recently referenced. So what happens is there is a timer, and operating system has reference bits, if you will, for each page in the page table. Remember, there's a reference bit or access bit that says this page is accessed within the last interval. And whenever the hardware accesses a page, whenever the processor accesses a page, that bit in the page table is set, saying that the processor actually accessed this page. So if you look at a page table entry, there are a bunch of bits. This was one of the questions, although I didn't expect you to add those bits. So you have a valid bit, you potentially have a dirty bit, modified bit, and then you have an access bit or reference bit, and then you have a physical frame number, and you have some access control bits over here. Let's ignore that for now. But this access bit or reference bit is set when the processor does a load or store to this particular virtual page number. And imagine that you have 2 to the 20 of these, right? Pages in physical memory. Some of them have their access bit set, some of them do not have their access bit set in the last interval. And whenever a new page needs to be accessed, needs to be brought into physical memory, what the operating system does is figures out one of those pages that are currently in physical memory and picks one that doesn't have its access bit set, which means that replace the one that was not recently referenced. And how does it do that? Basically, this is called the clock algorithm. You have this clock arm, if you will, that points to the next replacement candidate. And operating system looks at that next replacement candidate. Initially, it starts from 0. Looks at the reference bit, access or reference bit. If it's 0, it basically replaces this page and brings in the new page. Okay? If it's 1, then the operating system moves the arm and checks the access or reference bit of the next page in sequence. If this is 0, then it's replaced, and this one goes in to the particular page frame this was occupied, right? Basically, page frame number is over here. And this one is written back if it's dirty, obviously, depending on the dirty bit status. If this is, again, not 0, if it's 1, then the operating system moves to the next page and checks the reference bit of the next page in sequence. Make sense? So it's a sequential search to find the next page that has not been referenced in the past interval. Obviously, if you have only one bit over here, and if you keep referencing pages, at some point all of the bits, reference bits, get set. So you won't find a replacement candidate. So then the key question is, how do you actually reset these reference bits? So what happens is operating system has a timer that periodically goes through and resets these bits. Make sense? So this is a very simple way of implementing page replacement. It's called the clock algorithm. And there have been many variations of it. Today's Linux systems, for example, or Windows systems use variations of these clock algorithm to figure out what is the page to replace. And of course, your search can take very long if you have too many pages that have been referenced in the recent interval. So at some point, a solution to minimize the time for that search, or cap the time for that search maybe, after searching n number of pages, if you haven't found a page that has not been referenced, then pick the one that you ended up at and replace it. These are heuristics. You could make this more intelligent. An alternative would be actually to implement LRU across all of these pages, but that's extremely costly. Like figuring out which page is actually the least recently used page is extremely costly, right? Out of 2 to the 20. Remember, we looked at the complexity of it with only 4. If you have only 4 blocks, then there are 2 to the 4 factorial possible orderings, right? If you have 2 to the 20 blocks, you have 2 to the 20 factorial possible orderings. And you don't want to maintain that many orderings. That's bigger than the page table itself, probably. Well, I haven't done the calculation, so. Yeah, it should be, right? Well, okay. Okay, what's in a tag store entry? We've discussed this briefly, but it's very similar to, so this is the page actually. This is the page table entry, which was part of your question, what's in a TLB entry, right? What's in a tag store entry? In a cache, let's go back to hardware caches, you need a valid bit, you need a dirty bit, similarly to page replacement, because whenever you access a page, whenever you write to the page, you set the dirty bit, such that when it's being replaced, it gets written to disk. Right? Similar, in a cache, you have a dirty bit, well, in a write-back cache, we'll take a look at write-back caches. If you write to a cache block, the dirty bit becomes set, and whenever this cache block is replaced, this cache block is written back to the next level in the hierarchy. And there are a bunch of replacement policy bits, depending on the replacement policy. And these replacement policy bits can be part of the tag per block or part of the tag store entry for that particular set, depending on what kind of replacement policy you have. Well, I guess I missed something, which is the most important one, the tag, right? You do need to have a tag over there too. So dirty bit depends on whether or not you have write-back caches. Have you guys covered write-back caching in 213? Somewhat? Maybe? Okay. Let's cover it again, anyway. Basically, how do we handle writes in a cache is an important question. And one of the questions is, when do we write the modified data in a cache to the next level? Or do we actually keep modified data in a cache and keep it inconsistent with memory? Well, write to a cache says, do not keep the cache inconsistent with the next level. Whenever you write to the cache, write it to the next level as well, at the time the write happens. Write back cache says, well, you can keep the cache inconsistent with the next level. Basically, whenever you write to the cache, just write to the cache, don't write it to the next level. Next level could be the higher level cache or memory. And only when the block is evicted, write the dirty block back. So advantages and disadvantages to both. With a write back cache, the advantage is you have a block, and if you keep writing to that block, you can consolidate these multiple writes to the same block. Right? You don't need to expose those writes to the higher level. Let's say you have an L3 cache and you have memory right after that. If you have a write to a cache, you would be sending all of the writes to memory, every single write to memory, and you'd be wasting a lot of bandwidth. And as we discussed last time, the bandwidth, the amount of bandwidth you have between different levels gets progressively smaller as you get closer to memory. So that becomes an even more valuable resource. You do not really want to waste it. Write-back cache has the big advantage that if you're writing to a cache block over and over and over and over, these writes become consolidated in the cache and they never get exposed to the next level. So you save a lot of bandwidth. And bandwidth also means energy, so you save a lot of energy also. The downside of this is, well, you need a bit in the tag store indicating the block is modified. Basically, that's why you need this dirty bit. With a write-through cache, it's actually simpler in a sense because you don't need to deal with eviction of dirty blocks, right? In a sense, there are no dirty blocks in the cache. That's why you don't need this dirty bit. You always write to the next level. But the downside, let's go to the downside. It's more bandwidth intensive, obviously. You don't coalesce the writes. This is also called write coalescing or write consolidation. You don't coalesce the writes in a cache block. As a result, all writes appear to the next level. And you waste bandwidth, and this could waste performance also because once you waste bandwidth, you're not doing other accesses during the time you're actually writing to the next level. But there's one advantage to write-through caches, which we will talk about in a little bit more detail, or which will be more apparent when we talk about coherence. In this case, all cache levels are really up to date. Whenever you write to a block, assuming all of your hierarchy has write-through caches, there's no inconsistency between cache levels. Memory has the same copy as this cache. You haven't modified something out of sync with something else. This leads to consistency. Now you can have simpler cache coherence because you do not need to check lower level caches. If you actually, cache coherence is a problem that whenever one processor writes to a cache and another processor has the same data cached in its own cache, if you have multiprocessors, now you have an inconsistent data in different caches, right, for the same block. And this other processor that has cached that block in its own cache should get the correct data. And modern processors have coherence mechanisms to ensure that that processor actually gets the correct data. And that coherence becomes simpler if you have write-through caches. Because write-through caches enable that all levels are up to date in the hierarchy. You just need to check one of those levels to figure out what is the correct data for the block that's cached in multiple processors. So this will become more clear when we talk about coherence. We'll have a lecture on coherence and consistency. Make sense? Okay. These are interesting trade-offs. There's another issue with writes, actually. And that question is, do we even allocate a cache block on a write miss? Actually, you could ask this question for any cache block. Do we even want to allocate a block for this particular block that we fetch from memory? Do we want to put it into the cache? If the block is going to be reused, probably the answer is yes. If it's not going to be reused, then the answer should be no. And people have developed policies. But writes are a special case. And there are two possible cases. Do you allocate a block if you're doing a store and you have missed on that block because of a store? Or do you not allocate? Well, allocate on write miss policy says, yes, allocate. What are the advantages of this? Well, if you allocate on write miss, you can consolidate writes. Basically, this has kind of the benefit of write-through. It's not exactly the same as write-through. Write-through and write-back assume that you always allocate on write miss. Actually, no allocate, obviously, you don't have a dirty data, right? You kind of always write through. You can consolidate writes instead of writing each of them individual to the next level, right? If you allocate on write miss, yes?
What's a write miss?
Oh, write miss means, I didn't define it, I guess. On a write miss, if you're doing a store and you miss the cache, versus if you're doing a load and you miss the cache. Clear? Okay, that's the difference between reads and writes in the cache. See, here also, same thing. Write, any kind of write means you're actually doing a store.
So the logic behind allocating is that if you wrote to it recently, you'll most likely read to it soon.
So that could be one reason, exactly. Yes. Or you could write to it again, right?
But if it's not the latter, then it wouldn't matter because you shouldn't have it in cache. You could just write to the memory, right?
That's right, but then you waste bandwidth by
Because you
keeping writing.
use the consolidate.
Exactly, you don't consolidate. That's the first one, yes. So if you allocate on write miss, now you can keep writing to that block, assuming there are writes that are happening, other writes that are happening to the same block soon. And this is also a simpler mechanism because write misses that you get on a store can be treated the same way as read misses that you get on loads. The downside of this is this requires a transfer of the whole cache block. into the cache. And we'll see a solution to this in the next slide. Basically, yeah. If you not allocate on a write miss, this conserves cache space if locality of writes is low. Whenever you bring in a cache block with a store instruction, if you're not going to reuse it, if no read is later going to reuse it, then you wasted space. By not allocating, you can potentially improve your cache hit rate. Make sense? Okay. Hopefully these are simple, so you can think about it more. So people have developed sector caches to solve part of this problem. Basically, and actually this could be helpful in other cases also. The idea of sector caches is to divide a block into subblocks. You still have a large block, let's say 64-byte block, but you keep valid and dirty bits on a per subblock basis. And you keep the tag for the entire block basis. And this is called a sector. Basically have separate valid and dirty bits for each sector. Sector is also called subblock. So subblock caches, sector caches, they're the same, if you hear that. So what is the benefit of this? Well, now you can actually allocate space for the entire block, but bring data only for the subblock. Or write only a subblock. Which means that subblocks can be individually valid or dirty. Now you have more finer granularity management of the subblock. And people have used these caches. A lot of IBM processors have this kind of caches. And one benefit, think about the writes. Let's say you're writing to an array, you're streaming through memory, and you're writing to consecutive locations in caches, in the cache. If you're doing that, now all you need to do is actually write to a subblock, validate it, write to the next subblock, validate it, and make it dirty. Write to the next subblock, validate it, make it dirty. You never need to bring in the data, old data, for that particular cache, for that particular block into the cache from memory, because you're going to overwrite anyway. Let's assume that you're zero initializing a particular block. There's no point in bringing that cache block, the old value of that cache block, into the cache, right? Because you're going to overwrite anyway. So this kind of cache actually enables that bandwidth savings. If you're doing streaming writes, if you will, you basically construct the cache block in the cache without ever bringing the data from memory. Does that make sense? You do 8-byte write, 8-byte write, 8-byte write, 8-byte write, and that's it. You never need the old value of the block from memory. That's one benefit. I guess the other benefit is, if you're reading a cache block, you may not want to transfer the entire block. If you think that the locality, spatial locality, is not going to be high, you may want to transfer maybe only 2 subblocks. Or maybe if the bandwidth is constrained at the lower level because somebody else needs to access it, maybe you transfer only 2 subblocks. Well, in this case, that's okay, because you have valid and dirty bits. And then the remaining subblocks will be invalid. Right? And when you need them, when you actually access one of those subblocks, you get a cache miss. Right? Make sense? So this gives you more flexibility in what granularity of data you actually bring into the cache, and whether or not you even bring the old version into the cache. Okay? So this works, of course. The first benefit comes only if you're writing an entire subblock. Right? If you're writing to a portion of the subblock, this doesn't work because you need to bring in the remaining portion from the memory, because you cannot have only a portion of the subblock cached. Okay? So think about what the logic would look like to determine a hit or miss. Now the hit or miss is not just a tag match, but it's also, you need to figure out the valid bit and for the particular subblock you're searching for. Okay. Well, I guess we've discussed this. No need to transfer the entire cache block into the cache. It writes simply validates and updates a subblock. There's more freedom in transferring subblocks into the cache. A cache block does not need to be in the cache fully, especially if you think it's not useful. But this leads to more complex design. And if you're not careful, it may not exploit spatial locality fully when used for reads. Okay? Because if you always bring just one subblock on a read, basically you're getting rid of the spatial locality benefit you would get by bringing the remaining subblocks. Okay. Any questions? So centric caches are nice because it gives more flexibility, and it's used in many designs today. The upside is now you have the tag amortized across subblocks, right? You could imagine one good question would be, why not have smaller blocks?
Because of the tag.
Exactly, because of the tag. Because once you have smaller blocks, your tag size increases. That's the difference between a cache with smaller blocks versus a cache that has subblocks. Yes.
Also, you can imagine this one being like somewhat dynamic if you make the design more complex and how many blocks you fetch, depending on your workload. Whereas the other one, where you only change the tag size, it's fixed.
That's right. Yes. Although you could decide in the other one, let's say you have blocks, you could decide how many blocks to fetch.
For just the normal one?
Yes. Basically, you could do prefetching
Oh, right,
for that
yeah,
one.
yeah,
Right?
okay.
Whenever you have an access, you can say, I'm going to fetch the next few blocks also. In a sense, it's a similar problem.
Yeah.
Okay. Okay, there's another design choice in caches, which is instruction versus data caches. And there are two options that people have followed. One is, do you unify them? Do you keep instructions and data together in the cache, or do you separate them? Unified cache enables dynamic sharing of cache space. Whenever you unify different things, you enable dynamic sharing, right? Remember this from unified reservation stations, for example, versus distributed reservation stations. Whenever you unify the space, you enable dynamic sharing. Basically, this gets rid of potential over-provisioning that might happen with static partitioning. What does this mean? Basically, if you split, let's say you have a total of 128 kilobyte cache space. Do you split it 64 kilobytes across I and D caches, instruction data caches, or do you have a unified 128 kilobyte data cache, I plus D cache, if you will? Well, if, for example, you split it and your instruction working set size is only 1 kilobyte, you're wasting the remaining 63 kilobytes in the instruction cache. Right? And your data working set is 100 kilobytes, it doesn't fit into the 64 kilobyte cache that you've allocated to data. That's the problem with static partitioning of the cache space. Whereas if you have a unified cache now, both the instruction and data can fit in that cache. That's the upside. The downside, well, you could now get instruction and data thrashing each other, which means that there's no guaranteed space for either one. They can conflict with each other, and there's no guarantee that you have instructions to supply into the processor. And this is, in general, a problem. This is a problem. Basically, instructions and data interfere with each other in the cache because they share a cache. For example, this happens if you have 1 kilobyte instruction working set, and maybe 150 kilobyte data working set, and you have only a 128 kilobyte unified cache. Now your poor instructions may be kicked out from the cache because you have a lot of data that's being streamed through the cache. Okay. There's one other downside to separating instructions or unifying instruction and data caches. Instructions and data are actually accessed in different places in the pipeline, right? Data is accessed in the data cache stage, data memory stage, and the memory stage. Instructions are accessed at the beginning of the pipeline, at the front end. And these are actually far away from each other if you design a big machine. So if you would like to, the key question is, where do you place a unified cache for fast access? Well, there's no good answer to this. So because of this reason mainly, first level caches are almost always split. You don't see unified instruction and data first level caches. You usually see an L1I cache and L1D cache. Mainly for the last reason above, but also for other reasons, but this is really for this reason. Because you would like to, remember, first level caches are really tightly integrated with the pipeline. You want to get the instructions or data very quickly. And if you put the unified cache far away from the fetch stage, first of all, it takes longer to access. And if you're actually accessing it together with the data cache, now you need multiple ports. Right? Now you need to have a mechanism for handling conflict between instructions and data if you don't have multiple ports. So mainly for this reason. And second and higher levels are almost always unified. Although there have been processors that have second level data caches and second level instruction caches, especially if you have server workloads with big instruction working set sizes, it may be a good idea to have separate instruction caches. But usually they're unified. Okay. Questions? You can actually think about other things here also. For example, think about other types of data. Which data type cache is better? Is a stack better to prioritize in the cache? Is a heap better to prioritize? Usually stack references have better locality because you keep accessing the stack, right? So people have proposed mechanisms to kind of identify which data has what kind of locality characteristics and cache it or prioritize the caching of it. People have actually proposed stack caches separately. Cache the stack separately from other data because it has better locality characteristics. Okay, this is what I told you earlier a little bit. First level caches, both instruction and data, the decisions of these caches are very much affected by the cycle time you want for your processor. Which means that because you usually want a higher frequency, lower cycle time, these are smaller and these have lower associativity because they're very tightly integrated with the pipeline. And tag store and data store are accessed in parallel so that you can get data quickly. Right? We mentioned that in the last lecture also. You do serial lookup versus parallel lookup of the tag and data store. Second level caches, now this is a little bit farther from the processor, so they don't need to be accessed as fast, but you would like to get still reasonable latency. Remember the average memory access time equation that we discussed? To get high performance, you would like to have a good hit rate, and you would like to also have a good access latency, and these go against each other. Right? So these are usually large and highly associative. Latency is not as important. It's still important, especially in the second level cache, but not as important as the first level cache. So these can be bigger. And there's a third level cache. Again, latency is less important to going over to the third level. So usually second level or third level cache, actually this is probably not true of many second level caches today, because they're getting closer to the processor, but usually third level caches, tag store and data store are accessed serially for the reasons that we discussed last time. Because if you actually access the tag store and data store in parallel, if you miss in the cache, well, that's a wasted data store access, right? And if it's a highly associative cache, you're powering up the entire word line of the data store, and that's a lot of power consumption. Instead, if you access it serially, you first determine whether it's a hit or miss. And once you determine it's a miss, you don't access the data store. If you determine it's a hit, you know exactly which way it hit, and you can power up only that way, if you will, in the set. You don't need to power up the entire set. So even the hits are much more energy efficient if you access the tag store and the data store serially. Make sense? Okay. There's another design choice. Do you actually serially or in parallel access the levels, different levels? Do you start the second level cache access at the same time as the first level cache access? Or, that's the parallel access part. Or do you start the second level cache access only if you miss in the first level, only after the first level cache access completes? Now there are advantages and disadvantages to this also. If most of the time you miss in the first level cache, or a good fraction of the time, you may want to start the second level cache access at the same time as the first level cache access, such that you cut off some of the latency, or you hide some of the latency to the second level. Now the downside of this is, if you hit in the cache, this access is kind of useless, right? If you hit in the first level, the second level access is useless, and you terminate it. But that introduces additional complexity. It's not only useless, it wastes power and bandwidth. If you serially access them, well, you don't get that latency benefit, but now you have energy benefit, right? If you keep hitting in the first level cache, and first level cache hit rates are usually very high. Of course, this depends on your program, but if you are hitting 99% in your first level cache, it's better to access them serially. First determine whether you hit in the first level cache, and then, depending on that, decide whether or not to access the second level cache. If you do a serial access, which most processors today do, is second level cache does not see the same access as the first one. Basically, the locality characteristics that you see in the second level will be totally different. Okay? Basically, first level cache acts as a filter. For example, if a block is accessed a lot in the first level cache, it may not be accessed a lot in the second level cache. Right? Because first level cache absorbs all of those accesses to that block, and the second level never sees those accesses. In fact, it may not be a good idea to put the same block in the first level and the second level and the third level, because once you access in the first level, you may not need it ever again. And people have tried to develop mechanisms to exploit that. Okay, any questions? Caching could be really interesting, right? There's a lot more, but I'd like to cover, this is one of my favorite topics. How do cache and virtual memory interact? we've looked at the similarities between cache and virtual memory, how page table resembles a cache, how TLB itself is a cache, right? And now we want to see the interaction, because these actually need to be accessed together to complete the memory access. And that's the interaction between address translation and caching. So when do we do the address translation? Whenever you generate a load address or a store address or any address, right? Any virtual address, instruction fetch address, you need to do address translation to it. If you have caches, do you do this address translation or TLB lookup, let's say, before or after accessing the L1 cache? Any thoughts?
Before?
Before. Who votes for after?
Same time.
Same time? What else? Okay. I guess nobody wants to vote for after. Yes.
Well, it would make sense for before because you just said that it's so tightly integrated that it would be quick, whereas accessing the TLB or something may incur more latency than necessary.
That's right. So it would make sense to actually, this is accessing the TLB, so it would make sense to do it after, right? Yeah. So that you're giving an argument for after.
No, for before. But
For
you should
before.
have the L1 before.
Oh, doing the L1 before.
Yes.
I see. Yes. Yeah. So doing the address translation after accessing the L1 cache.
Yes.
Yeah. Yeah, that's an argument actually, because L1 cache, you want to get the data quickly. Maybe you don't want to deal with address translation until after you got the data. So these are all valid options actually, before, after, or in parallel, and I'll show you. Some examples of this. So in other words, is the cache virtually addressed or physically addressed? Because if you want to access a cache before doing the address translation, before accessing the TLB, you only have the virtual address. Right? You need to cache virtual addresses. If you do it after, you can cache physical addresses. But now your TLB is on the critical path of data access, and now you have longer latency to access the data that you need for the load. So this determines the difference between virtual and physical cache. A cache is virtual if it's accessed with the virtual address. A cache is physical if it's accessed with the physical address after translation. And it turns out there are issues with the virtual address cache. And we'll talk about those issues. One issue is a synonym problem. Basically, two different virtual addresses can map to the same physical address. And if this is the case, and if you have a virtual cache, now these two different physical addresses can be in two different locations, right, in the cache. Because you're managing your cache with the virtual address, which maps to two different physical addresses. Or sorry, yeah, let me get back again. That's the homonym problem. Okay, synonym problem says two different virtual addresses can map to the same physical address. If you have virtual cache, these two different virtual addresses will map to different indices in the cache. But you're storing the same physical address. They really should be referencing the same data. So the same physical address can be present in multiple locations of the cache. And if one of those addresses is updated, if one of the virtual addresses is written to, now you've actually modified this physical data over here in this location, but the other copy of the same physical data is not updated. So now you can have inconsistency in the data, right? Because you cached the same physical address in multiple different locations in the same cache, if your cache is virtual. Okay, we'll try to find solutions to this problem. This is a problem of this is a coherence problem basically. Because you have multiple copies of the same data in different locations, how do you actually keep it consistent? We'll see other solutions to the coherence problem, but this is a limited coherence problem. There are actually two kinds of problems when you have a virtually addressed cache. The second one I described, but we'll talk about it in more detail. Homonym problem is you can have the same virtual address, and that can map to two different physical addresses. Right? When can this happen? Any thoughts? No, you know virtual memory. So you can tell me when the same virtual address can map to two different physical addresses. Yes?
Two processes.
Exactly, two different processes, right? They have totally separate page tables, totally separate, well, not separate TLBs, but logically separate page tables. As a result, process 1 may have a virtual address 0, and process 2 may have a virtual address 0, and they can map to two different physical addresses. Right? Physical address 1, let's say, and physical address 2. You can think of this as like this. This is a homonym problem. Synonym problem, and this is easier to solve. This actually you can solve by, in addition to the tag, you keep the process ID also. That way you don't get a false match. So this happens actually in multi-threaded processors, for example. If you have multiple threads accessing the TLB and the cache, they can have the same virtual address, but logically, these virtual addresses are really different. So as long as you tag the TLB and the cache entries with process ID, then you can solve that problem, right? Or with thread ID. That's one rough solution, if you will. People have looked at other solutions. So that's easier to solve. Synonym problem is a little bit harder to solve because this happens within the same process. Different virtual addresses can map to the same physical address. Why could that be within the same process? Or across processes, actually, yes?
Maybe you're reading the same part of a file, and then the OS just maps.
That's right. Yes, that's basically one way of implementing memory mapping, right? Physical address file, let's see. Yeah, there are many reasons actually for this. First of all, different pages can share the same physical frame within or across processes. For example, you can have shared libraries, right? Across different programs. You can have shared data across different programs. You can have copy on write pages. You know about copy on write pages? Basically, for example, you fork a process, fork another thread. You don't copy all of the pages that you need from the parent thread, but what you do is you have a new, I guess, virtual address allocated to that particular thread, and that just gets mapped to the same page. And only when this thread writes to this page, then you make a copy of the physical page. Okay, physical frame. So there are many other reasons. The I/O reason was the one that you discussed also. The key question is, do homonyms and synonyms create problems when we have a cache? And this depends on, is the cache virtually or physically addressed? So homonym problem, but the potential problem is same virtual address can update different physical addresses at different times. Right? Because you have the same virtual address belonging to different processes mapping to different physical addresses. So the solution is, basically the solution is easy because you just need to ensure the updates are to the correct physical address. Basically, if you update with this process, you should be updating physical address 1. If you update with this process, you should be updating physical address 2. And you just need to ensure that that happens. And that happens by indicating, by ensuring that the currently running thread updates its own physical frame or physical address. And by, you can do this by ensuring that you have thread IDs. Synonym problem. The problem is, I discussed earlier, same physical address can be present in multiple locations in the cache. And the solution, one solution is when one is updated, the other should be either updated or invalidated. Right. That's one solution. There are actually other solutions that we will discuss. Okay. So let's take a look at it a little bit deeper with the synonym problem. Whether or not problems exist depends on if the cache virtually or physically addressed. What does this mean? Basically, there are two things that come from the address to access a cache, the tag and the index. Right? And these can both come from virtual address or the physical address. Okay. Let's take a look at several options that I showed you, discussed before. In this case, this is a physical cache because you access the TLB before you access the cache, so you have the physical addresses available to access the cache. In this case, this is the other option. You access the cache first, and then do the translation. The upside of this is now you don't have the synonym and synonym problems, right? And homonym problems also, because now your TLB can contain address space IDs or thread IDs, such that you never get the wrong physical address over here. The downside of this, it takes a long time to access the cache. You first need to finish TLB access, right? And we know that this is a critical path to get a load instructions data into the pipeline. The upside of this, it's very quick to access the data from the cache. So the load critical path is not a problem. The downside, well, you have all the issues that we have with the homonyms and synonyms, right? Another solution is this, in parallel, you mentioned, right? In this case, this is a virtual slash physical or virtual dash physical cache. You do the address translation together with the cache access. Basically, you virtually index the cache, but physically tag the cache. So you can actually have part of the cache physical, the tag is physical, but the access can start virtually with the virtual address. And this way, you kind of get the best of both worlds. Not fully. You still access the cache quickly, and the tag check requires the physical address over here, and get the data quickly into the CPU, but you still have the synonym problem, unfortunately. So you cannot get rid of the synonym problem. Let's take a look at that. So this is a physical cache. This is a demonstration of it, and we've seen this before. You have the virtual address. This is the page offset, if you will, and this is after TLB, you get the tag, and you index the cache with the physical address, and tag is physical also. And this is the tag store, and this is the data store. Which means that a physical address can be in only one location of the cache. Okay. Virtually indexed, virtually tagged. Well, in this case, you just take the virtual address, and TLB happens after the cache access. I'm not showing it over here. Both the index and the tag are virtual. Okay. Virtual indexed physically tagged cache is a little bit more complicated. Basically, you take the virtual page number and access the TLB, and while you're getting the physical frame number, you also use the virtual address and get part of the index from the virtual address, index into the cache, and the tags are physical. Tag contains the physical frame number. After your TLB access is complete and the tag store access is complete, now you have a tag here and the physical frame number here. If the tag matches the physical frame number, then you get a hit. Okay? Then the key question is, where can the same physical address be in the cache? Can it be in multiple locations? Well, now this depends on where you get these index bits from. So let's take a look. I'll show this in a little bit more detail, because it's actually fun. So what we're doing is, you have a virtual address, and you have a page offset. Let's make the virtual address a little bit bigger. And this is the virtual page number, right? And after translation through the TLB, what you get is the page offset remains the same, right? It's exactly the same. And what changes is the physical frame number. You get a physical frame number corresponding to the virtual page number. And what we're trying to do is to tag the cache physically. So this will be our tag in each tag store entry. But index the cache with the virtual address. Right? Does that make sense? Now if your index bits, if you pick your index bits such that they only come from the page offsets, there's no problem at all, right? Because it's as if you indexed it with the physical address. Because these bits do not change. These bits are exactly the same in the virtual address and the physical address, right? So if your index only comes from the page offset, you're good. It's exactly like a physically tagged cache. Physical cache, because these bits do not change. Does that make sense? So you can enforce this constraint and still have a virtually indexed physically tagged cache, and still get the benefits of accessing TLB and cache in parallel. And that's one solution to the problem. The solution to the problem is basically ensure that index bits come from the bits that do not change in the page offset. What is the downside of this? Yes.
You could end up like with a small index value, a small index range.
Yes, exactly. Basically, you can have only a small cache, right? Right? Yes. Why? Because, well, actually, there's a solution to that. You can have a small index. Actually, you're absolutely right. What you said was better than what I said. You can have only a small index range. That doesn't mean you can have a small cache. Small index range means your index, the number of sets are limited. Basically, limit the number of sets. limit the number of index bits, i.e. limit the number of sets in the cache. So let's do some calculations here. Let's say you have 4 kilobyte pages, which means that you have 12 bits here, and your cache blocks are 64 bytes. So you have, if you think about it as a cache address, only 6 bits at the bottom are the byting block, right? So you can have only 6 index bits, right? Only 6 index bits. Meaning you can have 2 to the 6 sets. That's a small cache. But you can still have a large cache by increasing the associativity, right? Does that make sense? Basically, if you use this solution, your cache size is limited to associativity times page size. If you ensure that the index bits only come from the page offset, your cache size has to be, your cache size is this, at most. Does that make sense? Do you see how I got this? Because you have 2 to the 6 sets times 2 to the 6 bytes per block. And the number of blocks per set is determined by the associativity. Right. Okay? So that's a problem. If you don't want this, and let's make that calculation, I guess. With 4 kilobytes, your page size is 4 kilobytes. If you want to have, let's say, 128 kilobytes first level cached, your associativity needs to be 32, which is a lot at the first level. If you want to have 64 kilobyte first level cache, your associativity needs to be 16, which is still a lot. Well, maybe 8 is reasonable. But if you have a direct map cache, then your first level cache size needs to be 4 kilobytes with this page size. Okay? So this is perhaps not a good solution because it limits the size of the cache, but it is a solution. So let's go back to this a little bit. Basically, this is what I showed you over here. Your index bits come from the page offset. That way you ensure that a virtual address never is in multiple locations in the cache. But this also limits the cache size to page size times associativity, or less than that. In this case, the cache, put it another way, if this is the case, if cache size is less than or equal to page size times associativity, the cache index bits come only from the page offset, and they do not change due to translation, because only virtual page number changes during the translation. And as a result, a physical address can be in only one location in the cache, because you essentially index the cache and tag the cache with physical addresses. Well, that's what a virtually indexed physically tagged cache is, basically. I've already described this to you. Okay? So we don't want this limitation. If we don't want this limitation, what can we do? Well, increase the index bits such that they span the virtual page number. Now you can have more sets in your cache. Right? I guess I can erase this because now you still have a virtually indexed physically tagged cache, but some of the index bits can now come from the virtual page number, not only the page offset. Now the problem is this. One or more cache index bits come from the virtual page number, and therefore they can actually change during translation. So synonyms can cause problems, because the same physical address can exist in multiple locations, and the update of only one leads to inconsistency. Well, let's take a look at how this happens. Right? If two virtual addresses map to the same physical address, now you can actually have them in different locations. Right? Before, it was different virtual addresses. Right? Actually, let me see if I have an example of this. Oh. Let's take a look. I actually have a longer example that we will probably go through later. But let's say you have, let's see. Let's make this a little bit simpler. Let's say that we have only one bit, that A is 1. You have only one bit over here of index coming from, that you're using from the virtual address virtual page number and indexing it into the cache. In this case, this bit can be 0 or 1, right? And these two different virtual addresses can map to the same physical address. So let's say you have a virtual page number. I'll abstract all of this with x, let's say. x0, this is the last bit, and these are the remaining bits over here. And x1. They both map to physical frame number y, let's say. It doesn't matter what frame number it is. Right? These are two different virtual addresses, virtual page numbers that map to the same physical frame number. But they go to different indices, right? The first one, VPN x0, goes to index 0 and whatever this remaining bits are, somewhere over here. The second one, VPN x1, the one that ends with a 1, goes to somewhere else, right? And if they both happen to map to the same physical frame number, well, they really have the same physical address in the cache, right? Physical address, let's say y, and physical address y. Which means that now if you actually do a store to this address, virtual page number x0 and whatever address that comes after that, you update this location. Let's say initially they're both 0. With this virtual address, you write FFFF here. The same physical address over here is not updated, right? It's in a different location. It's in a different index. It may be in a different index. Does that make sense? So that's the problem. You have a coherence problem, if you will, because the same physical address can be cached in multiple locations because your index bits are actually coming from the virtual address. Actually, it's coming from the virtual page number because this page number can change during translation. Right? Okay, so how do you solve this problem? Well, we've already talked about this solution. This basically avoids the problem, if you will, by ensuring that the index bits do not come from this here. The other solution is allow the index bits to actually come from the virtual page number from here, allow them to change during translation, but once you write to a block, search all possible indices that can contain the same physical block and update them with the same value or invalidate them. This is actually used in Alpha 21264, MIPS, R10000, and several other processors today. And the idea is, if the same physical address consists in multiple different locations in the cache, when you're writing to one location, you know all of the possible indices that can contain the same physical address. Because you have only a limited number of bits. They can only be located in a limited number of locations specified by the limited number of index bits that come from the virtual page number. For example, in this case, when you're writing to an address in x0, you also go and check if the same address exists in x1, because you know this index bits can change, right? And then, of course, you do a cache lookup that checks if the same physical address exists in this location. So you need to do a tag match. It may not exist because it may not be cached. If there's a match, then you also write FFFF over here, or what you do is you invalidate this cache block such that only one copy exists. This is the same thing as a coherence problem. When you have multiple copies of data, you need to keep them coherent. And in this case, it's nice because you know exactly where the other copies might be, because you know what index bits change. So let's say you actually had 4 index bits over here coming from the virtual page number. Well, now, virtual addresses that have index bits 0, 0, 0, 0, 0, 0, 0, 1, dot, 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 all the way up to 1, 1, 1, 1, can store the same physical address. Right? Basically, those indices going from 0, 0, 0, 0, top one, all the way to 1, 1, 1, 1, can store the same physical address. So you have 16 possible places where the same physical address may be stored. So whenever you update one of them, you need to search the remaining 15 ones. Now that's expensive, right? Whenever you do a write to one of them, you have to go do 15 cache lookups. Well, that's a problem. That's why you would like to minimize the number of index bits. That's why this other solution exists over here. Because there needs to be, if you would like to use this solution, there needs to be hardware doing this, right? On every write to a block, on every store to a block, you're searching the remaining possible locations where the same block, same physical block can be located in the cache. And the bandwidth consumption grows with the number of index bits that come from the virtual page number. So another solution to the problem is actually to modify the software or restrict the software such that this doesn't happen. So the first solution was restrict the cache size such that index bits do not come from the virtual page number. And the other solution is restrict the page placement in OS such that index bit of the virtual address is always the same as the index bit of a physical address. Does that make sense? This way, again, you ensure that you never have this problem because the indices coming from the virtual address are exactly the same as indices coming from the physical address. Does that make sense? And the OS can do that, right? Because what the OS is doing, whenever it's doing virtual to physical allocation, I think I made a mess here, but ignore this. You have a virtual page number, you have a page offset, and then you have a physical frame number, and you have the same page offset. Basically, the OS would need to know how many index bits actually come from, how many cache index bits come from the virtual page number, and whenever it allocates a virtual page, it ensures that it is allocated to the physical frame that has the same index bits over here. If you are taking 4 index bits from the virtual page number, and if the virtual page number that's being allocated is 0000, the OS picks a physical frame that has the bottom bits as 0000. So it restricts the placement of a virtual page in physical memory. This is called page coloring. You can think of physical memory divided into colors, different colors. And if you have 4 bits here, you can divide the physical memory into 16 different colors. The color of the virtual page needs to be the same as the color of the physical page. That's it, basically. So this is used in many Spark processors to do this, and they can have large caches this way. Well, there's a downside to this. Now you've restricted your page placement, right? A virtual address, a virtual page cannot go to any frame in physical memory. It can go to only to 1/16 of the entire physical memory if your index bits are 4. Does that make sense? It's a fun solution, actually. It's a nice solution to the problem, but there's a downside to it. And let's take a look at the advantage and disadvantage of each, actually. The first one we've already discussed. If you limit the cache size to page size times associativity, you have simple hardware, but now you have limited cache size, especially if you want to keep associativity in check. The second hardware solution, on a write to a block, figure out all possible indices that can contain the same physical block and update or invalidate them. It's beautiful because there's no limitation to cache size or the operating system in this case, but now it incurs hardware cost and complexity. Also, you need to have ports into the cache, or you need to steal ports from the cache when no one is accessing it to do this check. The third solution, restrict the page placement in the operating system. This leads to simple hardware. You don't need to do any of these, actually. But now you have limited OS flexibility. So perhaps you get more page faults because you're restricting your page placement. For example, you need to, whenever you bring in a page, virtual page, that ends in 0000, you can only replace one of the physical frames that end in 0000. So 1/16 of your memory is not available to you. This may not be a bad thing if your memory is huge, but if this actually affects your replacement policy, right? You're basically unable to replace from anywhere in your memory. Okay, so there's an exercise. I don't know if you guys want me to go through that. We'll take a break before we go through that. But this was from the EC 741 midterm exam in spring 2009. It's a long time ago, huh? You guys weren't here at that time. Yeah. Yeah, it used to be 740 used to be 741, and then we decremented the number by 1 and it became 740. And I'll probably go through this actually just to give you an idea of the kind of problem you may face in the future. But let's take a short break for 5 minutes. And let's come back at 1:55. No, make the same mistake. Resume. That's a good idea. So we have a byte-addressable toy computer that has a physical address space of 512 bytes. The computer uses a simple one-level virtual memory system. The page table is always in physical memory. The page size is specified as 8 bytes. And the virtual address space is 2 kilobytes. One question is, how many bits of each virtual address is the virtual page number? This should be easy, right? You can tell me what that is. So if you look at a virtual address, how many bits is it? It's 11 bits. Because it's 2 kilobytes, and it's byte addressable. And page size is 8 bytes, which means that 3 bits over here is the page offset, right? So virtual page number is 8 bits, right? Scream if I do something wrong. Because nobody screams yet. Okay. The answer is 8 here. How many bits of, and you get 1 point. The preview. How many bits of each physical address is the physical frame number? Well, you do the same thing for the physical address now, right? The physical address can be 9 bits total because it's 512 bytes, and 3 bits. Well, this is not meant to be. It's not to scale. 3 bits is the page offset, same thing, and 6 bits is the physical frame number. Well, the answer is 6.